Hi, welcome to Teardown Tuesday. I've got a real interesting bit of kit today because it's not something that you'll find in your average lab. They're pretty high priced and they're pretty obscure. What is it? It's a Source Measure Unit, or SMU, or better known as a SMU, and this is an Agilent one which we'll take a look at. There's not too many companies on the market which make these. Keithley are one of the main players. Agilent do a really good one. Yokogawa do another one, and well, you know, there's not too many other players out there. What an SMU or SMU does is it's basically a pretty accurate voltage and current source, 4-quadrant source, which I might get into in another video. And basically this one is a 6.5 digit voltage and current meter and voltage and source meter built into the one unit. What are they useful for? Well, things like semiconductor characterization. If you want to characterize, say, a lead, for example, then you can feed it with very accurate currents from this. You can measure the voltage, and then you can couple that into optical measurement units and measure the light output and characterize it. All those sort of semiconductor characteristic curves which you find in the data sheets, FETs, you know, transistors, other types of devices. How they get those characteristic curves? Well, it's using one of these SMUs generally. So they're really handy bits of kit, but not something you'd find in your ordinary lab. So thanks to Agilent, they've loaned me 2 of these actually. One that they're going to actually let me take apart, and well, they think they might have to recalibrate it after I take apart. I suspect not. I don't think it's that critical, but hey, that's just their policy. I take this thing back, I send it back, they'll get it recalibrated. So hey, maybe we can go as far as we want. So there you go. And this is a dual channel unit. This model is the B2912A. Comes in several models. This is the highest end unit. It's a dual channel one, so it's got the second channel on the back there. Dual channels is handy because you can do stuff that you can't do on a single channel unit. It's got 4-terminal measurement, all sorts of stuff, fancy graphical LCD display on it, and this one can go down to 10 femtoamps resolution. So anywhere from 10 femtoamps up to, you know, a couple of amps sourcing and measuring. As I said, 6.5 digit resolution on voltage and current. So you can sort of do the same job as one of these with, you know, some current meters and with some constant current power supplies and some 6.5 digit regular multimeters and network them all together and stuff like that. But these SMUs are just all built into the one unit, designed to cover a large range and up to hundreds of volts. For example, I think this one goes up to a couple of hundred volts as well for characterizing high voltage transistors, for example, stuff like that. So really interesting and really precision bits of kit. 6.5 digits, 10 femtoamps. Oh, beautiful. You can just smell the precision in this thing. So, you know what we say here on the EEVblog, don't turn it on, take it apart. So basically what we've got here is 4 precision instruments in one. First of all, it's a precision current source. As I said, from 10 femtoamps up to several amps. And also it's a precision voltage source, or a precision power supply. Basically anywhere from 100 nanovolts resolution up to a couple of hundred volts, as I said, depending on the particular model. And it's also got a built-in 6.5 digit voltmeter and current meter as well to measure all of those ranges. So, you know, really precise. We're talking, you know, 0.005%, all that sort of stuff. Really high precision, as you'd expect out of a 6.5 digit thing. So 4 instruments in one, and it can do 2-terminal or 4-terminal measurements as well. And because it goes down to really low currents, then we've got things like ground and, well, guard, so that you can get triaxial test cables and things like that, which we might go into in another video, actually using this thing in a real world scenario if you want to take a look at it. In fact, using these is a little bit unlike, it's a bit unusual, it's unlike a regular power supply and multimeter which you'd typically use. So thumbs up if you want to see a separate video on that. Anyway, this is a dual channel unit. It's got the one channel on the front, force and sense, so 2-wire or 4-wire selectable. And then on the back is just the secondary channel, exactly the same. It's got its own guard terminal plus mains earth terminal as well, GPIB interface, little fan, some digital I/O stuff, because these are designed, well, not this particular one, but SMUs in general are often designed and implemented in production test systems where they manufacture semiconductors. You know, when they say in the data sheet that this device is 100% characterized for its, you know, bias current or something, you know, for its base current or something like that, then input current, then they'll be using something like these SMUs, and you can actually get rack mount versions of these multiple channels. So you put them in a big 19-inch rack, and you might have, you know, 10 or 20 channels of these things testing a whole bunch of semiconductors tied into a big automated test system. So this one is more like a bench R&D use kind of one, but it does have those digital I/Os if you want to integrate it with sort of like a desktop kind of, you know, semi-production test or pre-production test or, you know, R&D testing scenario, something like that. You usually wouldn't get one of these benchtop ones if you were using them on the production test floor in a silicon fab, for example. Fully networkable, of course, and as I said, it's got a big graphical display on it which can data log and plot graphs and do all the usual jazz. Anyway, let's take it apart. And in case you were wondering about the price, well, if you have to ask, you can't afford it. This one's about $13,500. Of course, this one is the dual channel, fully optioned up one. So these things are not cheap, which is why you'll never find them in your typical, you know, lab. They're just, you know, you really got to have a very specific need for this thing. And as I said before, 4-quadrant as well, which I explain in a separate video, so it can source and sync current. Excellent, very useful bits of kit. And this should just slide out, I think, because there's only 2 screws on this. I'm liking this new Agilent gear that just slides open. Anyway, all right, I've taken off the handle here, and that should just, ta-da, slide out. Oh, look at that. Oh, look at that. Oh, beautiful. Well, you can just smell the engineering that goes into this. Ah, this beautiful board on the top here, beautiful on the bottom as well, as we'll take a look at. Looks like it's duplicated there, so of course you'd expect dual boards in this thing, one for each channel. Beautiful shielding on the top here, as you'd expect. Lots of beautiful shielding, lots of lovely cable routing going through here. That's for the mains switch. No, that's a soft button main switch on the top, but that's, I don't know. They've got something running from the back right to the front there. Oh, it's just lovely, 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 lovely. Might not be easy to take this sucker apart though. So, anyway, this could take a bit of work. Check out some of the interesting stuff we've got happening around here. Obviously some high voltage ceramic caps here, 3 paralleled up like that, and then 4 of them, 4 banks of those in series for a total of 12 ceramic caps there. They obviously doing this high voltage. We've got the bleeder resistors across here, or balancing resistors across here. I've done videos on these before, balancing resistors across the individual. These are high value. These are, these are 10 meg. Obviously, this is part of the high voltage power supply. As I said, a couple of 100 volts output. So clearly they're doing really belt and braces there. We've got ourselves some power diodes, so they could be some protection, something like that. Don't know what's going on under this bit here. This is interesting that it's got its own double-sided taped film on there to actually protect it. That might be interesting to have a look under there. And then of course testing of these things is a big deal. So this is for, you know, this is a built-in test connector for pre-testing, for example. That's why you pay a lot for these. They're not made in high volume. They're engineered incredibly well, and you know, it takes a lot to actually test and characterize these. And then we've got some other interesting stuff. A couple of big power resistors here by the looks of it. And look at the huge number of vias we've got stitching going there. So obviously they're trying to get, that's most likely not for low inductance. So that's trying to get the heat down to the other side. So they're using those as heat sinking. And then we've got more power devices over here, more power resistors. They could be sense. Maybe not sense resistors. I don't see any sense wires actually coming off them or anything like that. So we'll have a look. Probably part of, looks like power supply, 3.3 volts there happening. So maybe some part of the linear power supply. So they're relatively high values. They're 10 ohms a pop and power resistors. So maybe they could be doing some current sense happening on those, for example, for the inbuilt power supplies. I don't think that's part of the output circuitry at all. And there you go, I missed the labels there, plus 245 volts, minus 245 volts across that entire network. So we're looking at 500 volts there. That's why they've, parallel their series and parallel stacked these capacitances. They needed X amount of capacitance on there for whatever reason, and well, the only way they could do it, they needed ceramic for the stability, and the only way they could get that was to parallel them up and then series them up for the high voltage. And if you're wondering about that circuit there, that's just a quad comparator LM339. So obviously they're just doing some testing stuff and maybe getting some pass-fail results out of here or something like that. And you can see on the bottom side board here, exact duplicate of the top board. So obviously one of these large full-size boards for each channel. That's why you pay a lot extra for the 2-channel unit. It's not like it's just built in. They've got to build in this whole extra board for that. So that's why you pay, a couple of thousand, at least a couple of $1,000 more for that. Complete duplicate. We've got another board here. It looks like, processor, big BGA device on there. That's probably running the OS. That would be the embedded computer, would be my guess. We'll take a closer look at that. And then we've got some more processing on the back here. That looks like that's the GPIB board. Dead giveaway. There you go. It's all on the one board. GPIB there. That'd be our GPIB chipset. Or curiously, going down into the main channel board down in here. So that could be just using that as a convenience and then bypassing that sort of stuff maybe through to the front and coming out these ribbons here and into the main processor down here. And there you go. That's just, as I said, a plug-in processor module. And there we go. It's a Spear ARM processor, of course, we've seen before. Very common. We've got a Xilinx Spartan FPGA on there. So that's presumably doing all the main processing, running all the main OS and whatever Windows CE embedded thing. Very smart to put that on a card. They can just upgrade that later because all this analog stuff doesn't go out of style. They want to manufacture this for the next 15 years. So this stuff doesn't go out of style, but this stuff might. They may have to upgrade this at a later time. And I figured out why that other metalwork on the back had that plastic on here. It's just a duplicate of that. So obviously they're using it on that side, plugging into that card edge connector on the front panel, but they're not doing it over here, but they're just duplicating the metalwork on the other side, and that's why it's there. They've just got the same part. And it looks like we might have a relatively easy time getting this board out because look, it obviously undo a couple of screws and then it slides forward like this and then pops out. We've seen this construction before, and that's at a couple of points, 3 points along there. So hopefully undo a couple of screws in here. This board just slides forward like this and then lifts out once you undo the ribbon cables. Curiously though, I do see a bodge, and it looks to be a ground bodge, and it's soldered directly down. It's scraped off some of the solder mask down on that screw terminal there, and they've taken that, snaked it obviously all the way through over to this point over here, which has a diode which we'll probably be able to get in and have a look at. But yeah, bit of an afterthought there. And I gave that a little tug forward, and it looks like it is going to pop out exactly as expected, hinged out. Yeah, we've got the wiring. That's connected in there like that. We should be able to You get that, oh, you know, probably best just to undo the connector there. And there's a couple more under here, but we should be able to get those out and just lift out the board. Brilliant engineering, look at that. And that is just beautiful. Look at this heatsink here. Beautiful RFI gaskets on the bottom of this. So when this flips up, goes in there, makes excellent RFI contact with the chassis down in the center there. We should be able to do likewise with the bottom board. That'll just sort of like pop out and it'll just have this center chassis held in there. Oh, it's just gorgeous. It really is. So really the only I/O on this board, this wire coming along the top here, that's obviously the power connector going to the board, so that'll be coming out of the switch mode power supply, which we'll eventually take a look at. That's in its own well shielded enclosure here, it has to be. And then all we've got is the output connectors here. This is for the second channel on the back here, so this top board, if you bought a single channel unit, of course, none of this would be populated inside here. You wouldn't get this top board and you wouldn't get this all the connectors on the back panel, which pops out in its own little back panel there. So they just put a blanking plate over that for the single channel model. But there's nothing, and basically, and then as we said before, all the stuff goes from the ribbon cable up here over to the main processor board, over to, well, the front panel board, which is not only used for the front panel, the display and the connectors and stuff like that. It's got battery backup in there as well. But then that obviously there's a then the processor board is on the bottom of the unit, which then plugs into that front panel. So really very simplistic interface, and that's how you want to design it. You don't want to have cables running every which way over the shop. DC input, you got your I/O connectors, and you got your connection to your processor. Very well thought out. It shows that they were thinking about the system design of this thing when they actually laid out this board. It's not like, you know, some guru designed all of the analog stuff on here and went, I'm just going to lay out this board and I know what I'm doing, and then just whack it in there and then have to run cables all over the shop. No, they really thought about how it was going to be integrated with the front panel and everything else. Fantastic. A lot of engineering hours went into this, let me tell you. And our channel board here, pretty easy to understand just looking at the physical construction, as you can usually do with teardowns like this. Look, we've got our DC input one over here coming from the DC to DC converter. It's not marked, but it might be, you know, 12 volts DC or something like that. Looks like it's fused. Got, yeah, big nice inductor on the input. Everybody's happy. Big high voltage step up DC to DC converter here, because as I said, this thing has a maximum output voltage of like a couple of 100 volts, like 200 odd volts. So that's why they needed to generate that high voltage we saw before. Here we go. We need to generate the plus minus 245 volts on here, for example. That ultimately then goes out. So here's our power supply under here. This will all have the local voltage regulation as well, you know, 3.3 volts or whatever, to power all the digital and the other analog stuff under here as well. We'll probably have plus minus 15 volt supply. They'll all be very low noise linear regulators, of course, local regulation. When you're talking about currents like, you know, really 15 femtoamps or whatever it is, absolutely incredibly low. So you really have to look at low noise local linear regulators. But anyway, high voltage regulation, step up DC to DC converter. That's the output filter into that. We're generating now plus minus 245 volts there. Probably got some sort of load or something there to keep it all nice. And then we've got some other control or regulation around here. No, it's saying plus 20 volts here. So yeah, plus minus 20 volts. So there you go. There's our local regulation. I don't know why it's sort of all the way up this end, because I would have expected the high voltage to flow from over here and then power the output side of it. But anyway, they've got plus minus 20 volt rails there, most likely for the analog, all the analog stuff. And then because they don't need any of that shielded at all, which is why all this stuff out here is just basically the power supply to get the thing ready to generate all the high or generate all the precise voltages and currents, which are of course under this completely shielded setting, both top and bottom. And obviously, because it can generate a significant, I think it's 10 amps at a couple of hundred volts, you know, so it's significantly wattage. It's maybe not that high. It's not a couple of hundred watts, but I think it's like 30 watts output capability, source and sink. So you need, that's what this heatsink channel is here for. Doesn't look like a heatsink, but there it is. It is a heatsink. They've got some seal pad underneath that. So that big aluminium extrusion there is connected to your power devices, which look like they're on the top part of the board here. So these are the screws likely that hold down those power transistors in there, coupling them down into the heatsink on the other side. And of course, this is where your thermal management comes in. Here's your fan at the back here, okay, which got some shielding tape over that. Look at that. That's attention to detail for you. Don't want to muck up your EMI by, you know, having that big fan, that big path in there where things can get in and out of. No, they've shielded that puppy. Anyway, we've got ourselves a fan guide here, top and bottom. So this one, there's obviously a mating one on the other side, because as I said, there's another channel in here for the other channel board. But here you go. They're probably, I'm not sure, yeah, they would be blowing out. So air would be coming in the side. Yeah, air would be coming in the side of the units here, I suspect, and then being blown out the back, I think, is the way it's set up. Yes. Air on the side of here. The case, as you may have noticed right at the start, had the vent holes on the side, and then sucking that through the heatsink and coming here. So that's why the heatsink is channeled, is open like that and is channeled like that, because then all of the air will be sucked right through the heatsink like that. Very efficient. Beautiful thermal design. You've got to think about that in something like this that needs, you know, 30, 50 watts of sort of power management inside, you know, a reasonably, you know, smallish closed case like this. But as for the heatsink though, it's interesting that it is on this side, the power devices are on the other side. It's not like they mounted them on the back side of this board with the tabs directly connected onto here. So they're relying on the screw going through there to get thermal coupling. They're relying on the sill pad. They've obviously got some exposed sections of the board, exposed copper on the board, and they're probably using hundreds of little vias in there. As we saw here, of course, hundreds of little vias to get power through to the other side like that. Not terribly efficient, not the most efficient way to do it, but good enough. And when you're constrained in this sort of, you know, case size and things like that, a lot of thought would have gone into that, a lot of measurements, a lot of testing to make sure that that was adequate. And now we'll lift the skirt on the, hey, there we go, the source and measure part of the unit, and look at that, there's a lot of nice stuff on there. Ooh, I like those. Look at those TDK lambda things. Oh, they're very nice. That looks absolutely beautiful, and some lots of guard traces happening around here, as you'd expect. Let's go take a close look at those, because you need those down when you're talking 15 femtoamps. Now we've got some really nice precision low level measurement stuff happening around here. Take a look at that. That looks for all the world like a coaxial read relay there. Fantastic. We'll take a better look at the part number. Little tiny QFN down in there. What a pain in the ass. But look at all the gold traces. These are all guard traces, and I've gone into guard traces on previous videos, but the reason that they're gold is because the solder mask has been left off, and that when you put those around a component or around a node, in this case we have a node here, for example, they don't want any surface leakage into that node. So that guard trace, that gold guard trace, will be kept at the same voltage potential as the point that they're actually measuring, so that any leakage going into here won't affect the critical node right in there. And this is one of the reasons why they think they might have to recalibrate this, because if I put my greasy fingers on there, and well, you know, guard traces can only work so much. I can actually probably affect the calibration of this thing if I started, you know, I'm spitting as I'm talking and it's all going all over this board, all over the shop. But yeah, probably shouldn't have to recal this thing, but this is where all the critical measurement stuff is happening. And check out that. Is that a capacitor there? Look at that. It's got its own little isolation slot under there, so they really didn't want any leakage from one side to the other there. It's not a high voltage isolation slot. That'd be a leakage isolation slot for sure. And there is our read relay, I believe. And you can see, look, the shield around that. I mean, there's our input and our output contacts there. And that sucker is shielded brilliantly. And then we've got our coils coming in on the bottom. So that'd probably be magnetically and electrically shielded as well. And just at a quick Google, I can't find any info on that. That part number does turn up as a relay, but it's not one of these sexy read relays. So I can't immediately find the data on that. If I can, I'll link it in. And then we've got our Kelvin connection relays here, and here's an internal diagram showing the physical connection of how the voltage and current sources and the 4-terminal measurement is connected on the output. And likely high voltage precision 10 meg ceramic resistors in here, that probably for the high range current measurement shunts. And if you're wondering what that little QFN is, well, try and decode that sucker. And just around that, we've got a couple of Fairchild FDS 8978 N-channel MOSFETs down in there, so they'd be doing some switching. And it looks like we've got some protection happening down in there as well. We've got ourselves our 4 diodes. They could be, you know, Zener type things in old style MELF cylindrical package, which I love. They would be incredibly low leakage, of course. Bet your bottom dollar. Probably cost a few bucks a pop. And clearly we've got some precision current shunt resistors down in here. There we go. That looks like 50 milliohms down in there. R050 there. 50 milliohms current shunt. Probably another one there, but it's, hey, it's upside down. Woohoo! Back to front. So there we go. That would be, are they tapping that off? Is this the amp for that? I don't know. Or are they tapping it off there? It looks like they might be tapping it off there and going off. But you can certainly see these are obviously MOSFET switches. You can tell by the pinout and also the the fact that big traces are running into the multiple pins. So they've got some high current switching, and this is another current shunt resistor of some description with the 2 taps coming off there. And then you've got your differential signal heading over there to some sort of precision instrumentation amp. And for all you volt nuts out there, yes, classic linear technology LM339. They're still making these things. They're still using everything. That's our precision voltage reference for this thing. So yeah, it does have that weird ass part number 1826-1249, but that is basically a rebadged LM399 manufactured by LT. And you also notice, yeah, of course this is going to have extensive built-in self-tests. So yeah, various test signals, what those test signals actually are, precision DC voltage sources or something like that. I don't know, but yeah, anyway, all of this is built in, and that's what adds to the expense of some really high precision bit of kit like this. And needless to say, they haven't mucked around on the capacitors. Quality Nichicon brand, 105 degrees C rated. Yep, spared no expense. And these beautiful looking TDK Lambda top quality bricks here, these are DC to DC converters. In this case, 9 volts DC in, 5 volts DC out, isolated. So made in Japan. They really haven't mucked around here. You can buy these on DigiKey. These are about $16 each in 10 of quantity. And really, they might only make, 10 or 50 of these units at a time. In fact, they might even make these units to order, so to speak. You order one of these and they might make, I don't know, 10 or something and fulfill the order. But yeah, very low volumes for these type of products. And really, they didn't want to roll their own. So they spared expense. Doesn't matter in something like this. You just want something that works. A designer's time shouldn't be spent dicking around on an isolated DC to DC converter like this. If you need it, go to someone like, top quality manufacturer like TDK Lambda, get top price off the shelf unit. It's fully characterized, you've got the full data on it, you know exactly how it's going to perform, guaranteed, whack it in there, job done. You're better off spending your time on all this fancy whiz-bang stuff over here. And yes, that is a Xilinx Spartan 6 on here. What is something like that doing on something like this precision device like this, a current and voltage source and measure unit, well, it's got arbitrary waveform capability as well. So I suspect that could have something to do with it. Perhaps another little Xilinx part over here, complete with separate JTAG headers for each one. So curiously, you can see the parallel traces running out of there through little, are they little R's and C's there? I can't quite see on the screen, into that little beastie over there. Is that like a parallel DAC? Would be my guess. So maybe this is generating the arbitrary waveform or parallel data out straight over to a DAC. Let's look at that number, see if my hunch is correct. I could embarrass myself here. And no, I wasn't wrong. These things were pretty obvious. There you go. It's a TX DAC in there. Pretty decent one. Going over to this TI OPA 1611 op-amp. No surprise for guessing, that's pretty darn schmick. In fact, it's designed as one of those audio level ultra low distortion ones. 0.00002% or thereabouts. I mean, geez. I mean, you fart halfway across the solar system and you're going to generate more distortion than this thing has. Unbelievable. And then no surprises for finding a digital isolator sort of coupled onto that FPGA to get digital data in and out while being completely isolated. ISO 724. And then there's the other. So we've basically got that coupling between the two FPGAs over here. This FPGA doing the arbitrary waveform stuff, maybe some other housekeeping stuff, who knows, but that is digitally isolated from this FPGA, which presumably drives all of the control side over here. And this is what this isolated power supply is powering. This section down in here, notice the white line there. The PCB design has been very kind to us and shown how they've separated the two halves. What are they? Well, they've even labeled them. vSense is up there. So there's our voltage sense path or voltage sense channel up here, and here's our current sense channel all the way down the bottom. And these have to be the ADCs. Let's go in and take a look at those. And sure enough, both of those are a real high-end ADC. In this case, a Texas Instruments ADS 16751. Let's go to the datasheet. I think you'll be impressed. And look at this beast. 4 meg sample per second, 24-bit Delta Sigma analog to digital converter. Here we go, 103 dB dynamic range at 4 meg samples per second, and down to 125K where they may be operating. I don't know if they would be sampling the full 4 meg sample here. They may be using it at a lower rate to get better performance, but 111 dB dynamic range, minus 107 THD, fantastic, 3 ppm. DC accuracy, beautiful. Well, not much, only 4 ppm per degree C gain drift. It's got programmable digital filters. The bandwidth is 1.7 megahertz, so it's right up there at the Nyquist limit, really, pretty much. So that's quite impressive. I like it, and it draws half a watt. And of course, there it is, test and measurement. That's what we're using it for. Got ourselves an interesting little resistor network there by the looks of it. Probably a precision resistor network, and by the color of the green, I'd say probably the same manufacturer as these precision resistors over here. And once again, we've got another one of those QFN packages, the same as we had down in this channel over here, and of course more guard traces going around there. Don't want any leakage at all into those nodes that they're measuring. And down in there, no surprises for finding a precision op-amp. It's more than a precision op-amp, it's an ultra-precision op-amp. 36 volt supply, 2.8 nanovolts per root hertz dual op-amp, analog devices, AD8676. Nice. Then we've got a couple of more analog devices parts there, don't know what they are, and of course some switching you'll find in here for range changing and stuff like that. And back over to the FPGA here, but going back to the digital side of things, how it gets all that information back to that main processor board. Well, no surprises for guessing that's galvanically isolated too. We've got another one of these digital opto isolators here. A couple of dip switches, I'm not sure what they're setting there, but you can see that the silk screen, that all of this stuff right up here is all electrically isolated, all outside here. That's what that silk screen is designating, and if you have a look on the bottom where it's going, there we go. There's some more, what looks like probably some more opto-isolators there, bringing data over to those ribbon cables, which then go over to the main processor board, and all of that designated by the silkscreen, electrically isolated. And let's flip this metal plate off here and see what we get underneath here, if we can get it off. There we go. Oh, that's all very nice and integrated. And ta-da, there's all our power devices, all surface mount ones. Then I thought there might have been maybe even some TO220s or something on the bottom going through those screws, actually getting that heat through. But no, they're all surface mount, and they don't have a huge number of vias around them, just a small number. I'll get in there and show you that closer up in a second. But anyway, we've got the various supplies coming in here. So if we start at this one here, you can see that we've got plus 245 volts here, plus 35 volts here, plus 20 volts, and then the other side of this, then we've got the negative supplies going in, minus 245, minus 35, minus 20, so various supplies for the various output ranges, and they'd be switching those through depending on which range you select. So there you go, that's rather interesting and very symmetrical for the positive and negative supplies, but that's what you expect, because as I said, this is a 4-quadrant device, meaning it can source as well as sink current. So they've got to have those devices symmetrical on the power rails like that. And this thing has current sensing coming out the wazoo, as we saw on the top side there, but we're basically being fed in here. Look, we've got 4 10-ohm power resistors there paralleled up, giving you 2.5 ohm current shunt resistance there, and then that's being tapped off by, I believe, that little tiny SOT23, that'd be like a high side current sense amplifier, and there's probably more current sensing going on in all parts of this thing. Plenty on the top side and plenty on the bottom. That's not for the direct output current, that's just for self-testing and all that sort of stuff, just to make sure everything's working fine. And no surprises for finding a real beefy quality high voltage N-channel MOSFET on the positive supply rail. In this case, the FQB 8N60C from Fairchild, and it's a 600 volt, 7.5 amp, 1.2 ohm on resistance MOSFET. Very nice. And as you can see, they've got 4 of these paralleled up. The drain connection, which is the tab there, they're all connected in parallel. But they've, of course, got their own current shunt resistor down here. So they're using these as basically a constant current load. That's pretty much what it is. And there's the current sense resistor side of that. They've got some extra range switching in here, which is rather interesting. 0.1 ohm resistor here, and then 2 separate 1.0 ohms. This is a dual N-channel MOSFET. That's a FDS 8978, and I presume, haven't decoded that number, but I presume that's a little MOSFET as well. So they can switch in any one of these current range resistors, and probably might have some current sense amp or something here, because they're tapping these off, so you can see the value being tapped off that thing, and that's how they're able to sense and maintain the precise current. So we've got our big N-channel power device up here, and then we've got our low side current range setting down here, and then that's duplicated all across there 4 times, all with the same values and same components. And here's a quick little Dave cat of how that all works. We've got our big N-channel power MOSFET up here. Of course, that dissipates all of the power, or well, a quarter of it anyway, because we've got 4 of these whole sections paralleled up like this. So this is our big power device, which sinks and sources our current here. And then we've got our range switching down here. So our current sense resistor, as you've seen in my constant current load, basically similar sort of thing, except we've got some extra MOSFETs for switching there. But of course, all of the current does actually flow down through here. It must flow through here. It can't flow out into the gate, so it's got to come down here. So these MOSFETs down here, while they're lower power and lower voltage, they still have to handle the maximum current. We saw this was a 7 amp rated MOSFET up here. These, and no surprises, this FTS 8978 is also 7 amp rated as well. So with these three range resistors here, you could get a reasonable combination of current range values, and of course then there, I didn't show that, but they would be tapping off the value from these current sense resistors, and then that's how they're able to regulate and maintain the current, and they're doing that paralleled up across all 4 sections like that. Really quite nice. Belt and braces, they've gone to town. And then on top here, flipped upside down, so all the electrons are going to run down to the bottom, get better performance like that, you know, higher power dissipation. Anyway, this is a P-channel MOSFET. This is a 25P06. So it's a 60 volt, 27.5 amp MOSFET. So it's a real beefy one. So obviously they're switching on the main supply there for all of these. These are your load resistors down here, but this is just effectively acting as a switch for all of your current flowing into all of these FETs. Now the product spec for this thing is only 3 amps max continuous DC current, but it can handle 10 amps constant current, pulse current, sorry. So really, you know, this thing is overrated in terms of, and so are these, overrated in terms of current handling capability, but that's really not the main factor here. The main factor would be the on resistance of this thing, and especially these, the power dissipated. And yeah, they probably could have handled this with just one device or maybe 2, but hey, you spread that heat across multiple channels, becomes much more reliable. And then over here we've got ourselves another P-channel MOSFET, but in this case it's a 500 volt unit, so another high voltage one which can easily handle the full supply capability of this thing. 1.5 amps, that is an FQB 1P50. So it'd be interesting to sit down and figure out the exact arrangement that they've got here for the positive half, with all the switching and load arrangements and current sensing and all sorts of stuff, because it is a little bit involved. I'm not going to sit down and do it now, but if anyone wants to go through the exercise, by all means, there is where the split is going to happen. Everything on this side is going to be for the negative supply rail, so it'll be an exact mirror image of what's happening with all these devices over here. And of course, you know, we've figured out our main load resistors, and we've got some, you know, we've got a low voltage and a high voltage switch on this side by the looks of it. Not sure what's going on around here, but yeah, it's very interesting arrangement. So I'd love to see a schematic or a theory of operation for this thing, because as I said, it is a 4-quadrant device. And you can tell that these ones up here are pretty much only switches because of the limited amount of heat sinking on there. So of course they're over specified for this purpose, so they're not going to dissipate much power if they're just, you know, slamming these things on hard and then just switching the current through to these devices. These are the ones, you can tell there's not much heat sinking because there's no vias around these that are dissipating the heat down into the other layers and the heatsink. They could have done that, but obviously they don't need to. So it's only these devices here which are taking all of the current, of course, and you don't know what your load's going to be. So these things have to dissipate a lot of power. That's why they've paralleled up 4 of them, and they've got that via stitching. I expected more via stitching than that to get the lower thermal impedance through to the other side so that they can get to the heatsink. But these are, you know, very over specified. So you know, it does the job. Obviously, maybe they've got some vias underneath the actual devices themselves. That's usually not recommended because that leaches solder away, and they often don't solder all that well. So, but I'm surprised there's not, you know, hundreds of the damn things like there was up here. See those? There we go. There we go. Bloody 100 each side or something like that. Crazy. So I'm just a little bit surprised at that. They didn't gild the lily there. We've got a high voltage isolation slot down in here just to protect it from this other low side stuff. And as I said, on the negative supply over here, it's going to be exactly the same configuration as before, except they're going to have everything reversed. So the N-channel MOSFETs are going to become P-channel MOSFETs. And ta-da! This is a bit surprising though, not the same brand Fairchild. So they've got an Ixis 10p, 50p in here. And once again, but it's a similar spec component to the positive side. It's 500 volt, 10 amp. It's a little bit higher current rated, 1 ohm on resistance. So very similar style MOSFET. MOSFET, and of course those ones up there, they were P channel before, they will be N channel now, the 30N60s. I don't even have to look those up. Check this out. I'm glad they've got the guard rings around here, because look at the residue left on the board there. Ugh, pretty horrible. You definitely need the guard rings when your manufacturing process leaves behind that sort of stuff. Not a huge deal. I mean, the guard rings are going to do their job, but, you know, it just looks untidy. And you might remember way back in the video how we said as part of the really nice systems engineering, they were having the ribbon cables come in over this side, and here they are over here, and they're just routing those right across the board all the way over to this side. And you can see the isolation, well, the ground is still the same. You can see the silkscreen mark right around there, so all of that is at the same, all this stuff around here is still at the same potential. So this is all the digital side potential of the board. So they're just running those right across instead of having daggy cables running throughout the thing. But that would have been easier from a system design point of view. But no, they've integrated them onto this board. Very nice. Alright, if you're anything like me, you want to see underneath that heatsink. No, there's the only thing, as I said before, is going to be, they're just going to have some gold exposed pads, a big thermal pad on the other side. So I've undone the heatsink, but yeah, it's not going to come off without a fight. Aha, there's nothing you can't fix with the application of more force. There we go. Ta-da! Each one, of course, electrically isolated, but nice and sticky. And aha, there you go. It was, yeah, too few vias under there. They have completely populated the bottom side of the bottom side of that D-pack there with vias. Look at them. Probably 100 vias in there or something. And as I said, the disadvantage with that is that the solder does flow through to this side, but that actually can be beneficial, because then you can get a lower thermal resistance coming through. So, pros and cons both ways. Solder leaching money shot. There you go. So there's the thing. I mean, look, we've got bubbles under there like that, so not the greatest thing, because that means that you're not getting, there's going to be air gaps around there where this thermal, this sill pad is okay. It does conform around these, but not entirely. It is going to be better if you're going to have a completely flat surface on there. This one's not bad. It's, it's reasonably flat like that. Of course, pros and cons both ways. If there's solder leaching coming through, of course, means less controlled solder on the top side of the device, because you've got to apply the paste. And if, well, a lot of it's leaching in through here and you don't take it into account, then you might get a poor or, insufficient solder on the top side to hold down your device. But on a power device like this, there's usually enough paste to go around. But anyway, some people like to do that, others don't. Others would have, I probably wouldn't have done that. I would have had all the vias around the outside part of it like that, and not had the solder leach through to the other side. But each to their own. And of course, if you're wondering why they've got these plastic spacers here holding down the heatsink, well, it's electrical isolation, of course. You can't have that heatsink, well, you could have it at some live potential, but generally you wouldn't. That's why they've got the sill pad on the bottom side. It transfers the heat, but it leaves it electrically isolated, and that's why, because all these devices need to get their heat out separately, and apart from these four devices, they're not paralleled up at all, so they all have to get the heat out separately. So that's why the heatsink is at no potential whatsoever. It's just floating. In fact, they've only got the one screw down here actually holding it down and making electrical contact through to the PCB. But in this case, they don't seem to have anything going to it, unless there is a trace on the top side. They might be holding it at some nominal potential perhaps, but anyway, you don't have to. Alright, well that's enough for the main board. Let's take a look at the rest of the chassis here. As the front and the rear terminal connections, this happens to be the rear one. They're practically identical. Looks like they've got shielded coax coming down to the rear connector here. Nicely heat shrunk. There's one of the sense wires going off there. We've got a nice big ferrite bead in there, a ferrite clamp, sorry, in there, and they're tapping those off very nicely. So you can see the guard terminal here, that's actually connected through to the force line. Yeah, that is the force line there. So the center of the force line, so the guard terminal is actually connected to the shield of the coax. Then that goes through that ferrite clamp up into here like that. So that's what the guard terminal does, and then you can extend that guard terminal further out on the other side with your triaxial leads. Those test leads that cost $1,000 or whatever. In fact, I might have some in the box somewhere. Let me have a look. And yes, what do you know, in the other box with the other unit that I'm supposed to use for testing, yes, we got the triaxial leads and some component test fixtures. These component test fixtures probably cost more than an oscilloscope, and all they are is a metal box with, a nicely shielded metal box, got some silk screen on the front, and basically a shielded component test box. So you put your component that you want to test inside here, and you hook them up with these shielded triaxial leads. And here's a triaxial coax connector if you haven't seen one in the wild, because they're not used too often. They're used in these low leakage, low current measurement systems. But apart from that, not a huge amount else. Anything that needs real critical shielding, you're going to use these triaxial coaxes. It looks very similar to a regular coax. In fact, from the outside, without looking at the end here, you really have a hard time telling that it would be a triaxial type. So we've got the outer shield around here, which is of course connected through to your regular coax body here, and that's going to be connected to mains earth. So that one, ground, physical mains earth ground. So that one keeps out the 50 hertz hum, but that's not good enough for these measurement systems. You also need another secondary shield inside there, so it's physically going to have its own braid inside the coax, and that's connected through to that inner ring there, and that one's connected through to your guard terminal. So that's connected to your measurement system common inside the instrument, and that's very important. And then finally, you've got your test signal in the center conductor. And of course, this thing doesn't actually have triaxial coax connectors on it. It's got those banana plugs, but that's what this is for. You just plug it directly in like that, push it in, locks firmly in place, and bingo, you've got your triaxial coaxes in here, so you can connect those through. And of course, you can see that the outer box, of course, this whole box here is connected, and the outer part of the coax is connected through to your mains earth, so that stops any mains hum getting in. And then inside that, inside your triaxial, the guard inside, the coax inside there, the shield inside there is connected through to your guard terminal, which is your circuit common inside your instrument. So therefore, you get a double shielding on this thing, 50 hertz plus your protection, plus your shielding through to your ground inside the instrument. And that's how you do proper measurements on these sorts of very low current bits of gear. So you'll find these triaxial connectors and these sort of things. Usually for your really precise stuff, they'll have a triaxial connector on the front panel. So all of your high resistance measurement units, like say the HP 4339B or something like that, or your really low current measurement units like some of the Keithley gear and stuff like that, and for this one, which goes down to 10 femtoamps, this is what you really need if you're measuring down at those sort of currents and those sort of leakage levels. Really important. And these aren't just regular coaxes. There's a reason these are expensive. You can say that they're not worth the money, but when you're testing a measurement system, you really need these. You can't just use ordinary coaxes. They're just too crap, too lossy. You need the proper measurement leads. So that is the proper way that you would test your component, and your component is going to sit inside this test fixture. Hey, we already have a LED in there. There we go. So I'll be able to do a video playing around with components here. So you feed in, it's just got a little internal wiring diagram. You can connect your LED or your transistor or whatever it is you want inside this thing, and Bob's your uncle. It's all shielded. It's all connected through the outer boxes. You can see that the wire's coming up there. That's all connected through to your mains earth, keeps out that 50 hertz mains hum. And then inside that, you've got your guard terminal going right up to your test connector on there. Fantastic. So that is the proper way to characterize a LED or a transistor or some other semiconductor device. And this test setup, even though it might cost thousands of dollars, let alone the $13,000 instrument, is how you get those characteristic curves in the data sheet that you see all the time. Now, I don't know about you, but I have no compulsive need really to get at and have a look at that main front panel board. There's nothing much on there. It's just driving the display and the connectors and the front panel keypad and stuff like that. Not very interesting. It's got a battery backup there for the real-time clock, and it just basically connects the ribbon cables through to the main boards and then through to the main processor board as we saw before. So I won't bother taking that out, and likewise I'm not going to bother taking out the second channel board on the bottom, because it's going to be exactly the same as the one we just extensively looked at. But we do want to look inside the power supply. So that shield just came off very nicely. It all clipped under there. Screwed down. Beautiful, beautiful, beautiful. Single-sided job, very, very simplistic, because as I said, I think it's just got, you know, 1 or 2 voltages coming out here. Incredibly simple. So just a universal switch mode power supply. Single-sided board, looks very well laid out. No problems whatsoever. Once again, Agilent likely didn't do this. It would have been a third party. There we go, we can just see inside there. They've got a label on there, third party. It could be TDK Lambda again, awesome. Anyway, the output is just a single 24 volt. That looks like 6.3 amps, I think. So you really don't get much better in terms of power supplies than TDK Lambda. And, you know, first class as you'd expense. They've spared no expense. This thing would not have been cheap at all. But hey, in a $13,000 instrument, it doesn't matter. They're not pinching pennies. They've got proper Nichicon caps, of course. The mains wiring over here, of course, is properly crimped and then shake-proof washed down to the side, and they've got all the requisite input protection and everything happening. Beautiful, spaced out, and it'd be super duper reliable and would last, well, not forever, but a long time. And easily repairable too. So there you go. I hope you enjoyed a look inside that high-end Agilent B2912A Precision Source Measure Unit, or SMU as they're called, because you don't get to look inside these things every day, and yes, it does look like it works. 10 femtoamps and 100 nanovolts resolution up to a couple hundred volts. Unbelievable. Thank you very much, Agilent. And yes, I do have 2 of these units for a little while longer, so if you want me to do a video showing you how to use one of these things and playing around and maybe characterizing that lead they gave us, or something else, please let me know. Leave it in the comments. It's boot in. It's boot in. Will it work? Will it work? I'm sure it does. I'm sure they don't have to recalibrate this thing. I don't think I spat on it too much as I was talking, or didn't get my grubby hands on those critical nodes in there. Anyway, they've got those beautiful guard terminals. Should take care of it. Anyway, hope you enjoyed it. If you want to discuss it, jump on into the EEVblog forum. The link is down below. And also, if you want to see the high-res teardown photos for this thing, the link is down below as well. But it's on the EEVblog.com website. So, hope you enjoyed it. If you did, give it a big thumbs up, and thank you very much, Agilent. Catch you next time. It's pretty sad these things have to go back. They're sex on a stick, really.